Hi, everybody. This is Mrs. Lonroth, and I hope everybody is out there doing well. Today, we're going to do some notes. Please remember that if you have any questions about anything, you can get a hold of Mr. Kaczynski or myself, and we're going to have some Google Hang hours that we're setting up. So make sure that you pay attention to that and get a hold of us if you have any questions. So if you would get your lab book out, we're going to look at our lab results a little bit and then use that to develop a relationship between some of the variables that we looked at in our lab. So going to put the date up here at the top. It's going to be the 31st, and we're in Unit 9. And we're going to be talking about Ohm's law and power today. Okay, so just as a little review, the major variables that we've been looking at so far are voltage, which we use a capital letter V for, current, which we use a capital letter I, which is originally how it was measured as intensity, but it's current. Some people like to think of it as like a wire that the current would flow through, like a line, and then resistance, which is capital letter R. So let's look at our lab results. We had two parts of our lab. So let's start looking at part 1. And in part 1, we temperature, voltage, and current. So we changed the voltage up and we saw what effect it had on the current. And this was pretty straightforward when you did this in the lab. If you had the voltage, your independent variable here, and your current here, you got a nice straight line. It should have been close to going through the origin. So we get a pretty clear linear relationship. So that means that the current is going to be proportional to the voltage. If you use a bigger voltage, you're going to get a bigger current. If you use less of a voltage, less current. And if you think about voltage as the push, that's kind of in quotation marks, like it's the energy per charge, but it's what drives the charge through the circuit. So it makes more sense that if you're pushing it harder, it's going to flow faster. There's going to be more current going on. So when we look at the mathematical model you should have gotten, I'm going to show a little example here. This was the one that I got from my data. My mathematical model was I equals 0.03062 amps per volts times voltage. And most everybody got really good results on this, but it's a really, really, really small number. And one of the reasons why we do this is to try to really make sense of the slope. So we really want to know, what is that slope telling us and what is the meaning? But I think we're going to have to come back to that a little bit because I don't think it's quite clear yet what that really, really small number could be talking about. So let's skip. I'm going to leave a little space to go back to that, and let's look at part 2 of the lab. Part 2 is a little bit more complicated, but the results are actually a little bit more clear-cut. We looked at resistance and current. So keeping the voltage constant, we changed the different resistors and saw what kind of current resulted. And we did not get a linear relationship. So before you linearized it, when you had current here and resistance there, you got this kind of a curve. No, you didn't get that kind of a curve. I take it back. You got this kind of a curve, which is an inverse relationship. And when you looked at the blue sheet to see how to linearize that, it would say to plot, replace the x value with the inverse of the x value. So if you, instead of using resistance, you used 1 over the resistance against the current, then you'd get a nice line right like that. So we got an inverse relationship. And an example of that from some data that I had would be something like current is equal to 1.93 amp ohms times the 1 over the resistance. So that number 1.93 is a little bit more of a number that seems on the scale of things that we were looking at, and it rings a bell to me because I was trying to keep my voltage at around 2 volts. So if you look at the number 1.93, that's really, really close to the constant voltage that I had. And I would like you to maybe take a second and well, we'll do that a little bit later. I take it back. The slope, when you talk about the slope, meaning the slope should be or is the voltage that was kept constant. Running out of room there. It's this voltage that was kept constant. So if instead of that number we put voltage, we would get I is equal to V times 1 over R. So we're taking our 3 major variables and finding a way to relate them to each other. Now, let's go back up and look at part 1 then and see if we can make sense of the slope. Up in part 1, we had current and voltage that we were looking at. So if we come back up here and look at this, I'm going to erase that, but just to take your attention up there. And then you look at what we have down here with I equals V times 1 over R. So up here, if we said I equals V times 1 over R, then the V is over here, and that would imply that perhaps this resistance is 1 over R. Okay? Does that make sense? Because again, looking down here, I equals V times 1 over R. Up there, that would make sense that I equals 1 over R times V. So let's look at that. What would I get if I took 1 divided by my slope? If over here I did 1 divided by 0.03062. And if I do that, I'm going to get 32.7 ohms, which the actual resistor that I used was 33 ohms. So right there, we're seeing that, oh, that's the thing that we kept constant in part 1. In part 1, we kept the resistance constant, changed the voltage, and saw what it did to the current. And the slope is related to that value that we kept constant. And then in part 2, again, the slope was related to the value that we kept constant. In that case, it was the voltage. So we really wanted to find the relationship between these 3 variables, but you can't do 3 things on our axis, and we're not going to do the complicated math it would take to try to look at all 3 of them at the same time, but they're actually reinforcing each other. So if you want to take and pause the video in a second and go and look at your results and see if you take the inverse of your slope for part 1, are you getting a value that's close to the constant resistance that you used? And in part 2, is your slope close to the value of the constant voltage you used? So why don't you go ahead and pause the video and just go back in your notebook and see if that's true for you. All right. So I'm assuming that worked out well for you. If it didn't, you can ask me questions and I can try to troubleshoot with you about it or something like that. So this relationship, I equals V times 1 over R that we came up with, if we put that together, that actually is a statement of the mathematical relationship of Ohm's law. So Ohm's law, after our George Simon Ohm's law is that the current in a circuit is directly proportional to the voltage and inversely proportional to the resistance. Oops, that's it. So mathematically, that's saying that I is equal to V over R, which is just what we had up here, just combined together algebraically. V times 1 over R is the same thing as V over R. Erase that. Or more commonly, we put it into the form of V equals IR because that's easier to deal with mathematically. So this is what we would say is the mathematical form of Ohm's law, which is our workhorse of the unit that we're going to use over and over again to when we look at different kinds of circuits, when we start looking at things with multiple resistors, et cetera, et cetera. But I do want you to keep in mind that this right here gives the relationships a little bit better. It shows that the current, which is the dependent variable, is going to be directly proportional to the voltage and inversely proportional to the resistance. So you can see the connection between the words of Ohm's law and the math of Ohm's law in the mathematical model. I is equals V over R, but the V equals I over R is actually a lot easier to use when you're solving problems and you have less problems with algebra and stuff like that. So when in practice, we tend to use I equals V, or V equals I times R. All right, so we're almost there. Don't have much more to talk about. I do want to talk a little bit about power. All right, and then tomorrow we're going to practice with some of these things, but power. Now we talked about power in our energy unit, right? We use the letter P for power, and the units were watts, capital letter W. And in circuits, we're going to describe or define power as the rate energy is used in a circuit. Now, in our energy unit, our equation for power, a model for power, was change in energy over time, which is the rate that energy is changed or is used or changed from one thing to another. In our case, we're really talking about electrical energy that's used to power something, so it doesn't really come back. We don't think about it as terms of conservation so much. Our mathematical model for power is in circuits because we don't want to deal with time and energy and things. We want to deal with current and voltage and resistance. And it turns out that power turns out to be current times voltage, P equals IV, which doesn't look at all like energy and time when you look at it. But if you think about what each one of those, the current and the voltage, what they mean, the current is actually how much charge per time goes by a certain point, because it's how fast the charge is moving through the circuit, the flow of charge, how much charge per time. And then the voltage is the energy per charge that the charge will get from the voltage supply or from the power supply or the battery. And so if you took charge per time and multiplied it by energy per charge, you can see here that the charge is going to cancel out because you have a charge on the top and then a charge on the bottom. So if you take and multiply those together, you're actually going to get energy divided by time, which is exactly the same kind of thing that we were talking about in the energy unit. So even though current times voltage doesn't seem like it's the rate that energy is used, it actually is. So that is our mathematical model for power. And that's it. So 15 minutes. Hopefully that wasn't too much to talk about or to follow. Mr. K and I will be available. You can check on the Canvas webpage to figure out when we're available. Everybody take care of yourselves, and if you need anything at all, please reach out to me. Bye.